right, so we're going to start doing circuits. So this is electric circuits 1. The first thing we have to go over are some of the symbols and the types of things we're going to be talking about. So we've already talked about charge. What was charge? What did charge tell us? You remember? It was last week. I know it was a long time ago. Yeah, so electrons have the property of charge. Other particles also have the property of charge. Protons, electrons, things like that. And if you have two charges and they're oppositely charged, what happens? They attract, okay? That's basically what I want you to remember about charges. Also, their units are called coulombs. Current, does anybody know what current is? The flow of electrons, so the flow of charge. So when charges are moving, there's a current. And so we're going to use the symbol I for current. So C is already taken by something else. We couldn't use C for Q or I. For charge or current. So it's I, and its units are amperes. Symbol is an A. Then we have something called the potential. Symbol is V, and its units are volts. Anyone have an idea what the potential is? Yeah.
How many electrons can flow?
Yeah, so the potential is it creates the ability for the electrons to flow, so it helps create a current, yeah?
The difference between charge from one side to the other, I guess.
Yeah, so if you have a battery, there'll be a potential difference across the battery, which will help the electrons flow. Good. The next concept is power. It has a nice symbol called P, and its units are watts. Does anybody have an idea what power is?
Energy over time.
Yeah, energy per unit time. So it's the amount of energy you're getting per unit time. So, what's an example of something where you want high power?
Fast cars.
Fast cars, right? You want a powerful car. You want as much energy per unit time. You don't want that energy given to you slowly. You want it like right now, right? All right, and then there's circuit elements. So this little bar with a big bar on top is a battery. It supplies the voltage or the potential difference. The next one is a resistor. It's just a little squiggly line. I usually put the R by it to give you the resistance. The next one is a voltmeter. What does it measure? Volts, right? Yeah. Then we have a light bulb, a little loop with a circle around it. A light bulb is basically a resistor, but it also does what? What's the difference between a resistor and a light bulb? It produces light. So the other thing to keep in mind about light bulbs is you typically don't want to use them as resistors in your circuit element because their resistance isn't constant. So as they heat up, their resistance increases. So they're not a constant resistance. The next one is a switch. So it's a little bar here that kind of looks like a switch. If you push down on it, it closes the circuit. And ammeter. What does the ammeter measure? The current, yeah, the ampage. Any questions so far? Good. All right, so now we get to Ohm's law. So Ohm's law says that the voltage is equal to the current times the resistance, or V equals IR. And this is sort of one of the big laws of circuits. It's kind of like F equals MA for circuits. So I drew a simple circuit here. I have a battery, which supplies the voltage, and I have a resistor, which supplies resistance. And the battery is going to drive a current through the circuit. And the question you might ask yourself is, for a certain voltage battery, say I got a 2-volt battery, and a certain resistance resistor, like a 2-ohm resistor, what is the current in my circuit? 2 volts. I'm just kind of making up numbers. But the point is you can use Ohm's law to figure that out, right? So if you solve this for I, I is equal to V over R. And so basically Ohm's law is a way to determine the current in the circuit. All right, so another way of writing that is that current is proportional to the voltage. So if you double the voltage, what happens to the current? It also doubles. So if you add another battery, for instance, you increase the current. All right, also if you add more resistance, if you double the resistance, what happens to the current? It reduces by half. So if you want to reduce the current, add more resistance. You could also take out batteries if you have many batteries in it. Usually you just have one battery. So the best way to reduce the current is to increase the resistance. All right, so if we plotted this as, on the y-axis current, on the x-axis the potential, which is the number of batteries basically, what will we see? Straight line. As we add more batteries, the current increases. And this is what you're going to do today. You're going to do 1 battery, 2 batteries, 3 batteries, 4 batteries, and every time you add a new battery, you're going to see the current increase. All right, once you plot that, can you figure out what the resistance of the resistor was? Yeah, we can. What is it? It's the slope, yeah. Which is also equal to rise over run, right? But in this case, the rise is I over, help me out, V. Is that the resistance? Not quite, it's 1 over the resistance. So whatever that number is, invert it, and you got your resistance. So that's the experimental resistance. And then you're going to look at the resistor and compare. Calculate a percent error. All right, so I probably should have put up here resistance. Symbol is an R. Its units are ohms. It has this funny symbol. So capital omega, it's a Greek letter. Those are ohms. Any questions? Pretty simple, yeah? Add more batteries, see the current increase. All right, so let's make it a little more complicated. Let's add 2 resistors. All right, so we have a battery. It supplies the voltage, which is going to drive the current. And then we have 2 resistors. And the question is, well, there's 2 questions. We're going to measure the current going into resistor 1. And we're also going to measure the current going into resistor 2. The way you use the ammeter is you put it into the circuit. So you literally have to break off the wire and put it in and complete the circuit. So this guy is in the circuit, this ammeter. What's this ammeter going to read? Yeah, the current which happens to be I. All right. What about over here? If I put the ammeter over here, what's it going to read? Same thing, I. And if I put it over here, what's it going to read? The same thing. So what does that mean? That means that I1 is equal to I, which is also I2 is equal to I. So they're all equal. Why are they all equal? Because they're in series, because there's only one way for the current to go. It's stuck in this loop. Conservation of charge, you're not losing current. So it's all stuck there. So everywhere along this whole loop, the current is constant. You're going to do that and verify it today. You're going to see that that's true. All right, the second thing we can do is measure the voltage. So I'm going to erase these for a second. We can measure the voltage across resistor 1. All right, we can measure the voltage across the battery, right? What are we going to find? The voltage of the battery, okay? So we can also measure across resistor 1 and resistor 2. And what you're going to find is that the sum of the voltages, V1 plus V2, is equal to the voltage of the battery. All right, so if you measure across resistor 1, find that number. Measure across resistor 2, find that number, sum them up, you'll get the voltage of the battery. That's in series. Any questions? All right, notice how I set up the voltmeter. It's across the element. This is called in parallel. All right, if you put it into the circuit, it's going to give you a bad reading. Voltmeters don't like being in the circuits, ammeters do. All right, parallel. So here I have a battery driving a current, and then it splits up here and goes to 2 resistors and then comes back together and goes back to the battery. All right, let's do voltage first. So if I measure the voltage across the battery, I'm going to get V. What if I measure the voltage across here? What am I going to get? Turns out it's going to be V. So V1 is equal to V. If I measure it across here, I'm also going to get V. So V2 is also equal to V. So all the voltages are the same. All the potentials are the same. The next question you'll ask is, what about currents? So the current here is I. It's the total current. And then we have a current going through here, which I'm going to call I1, and another current going through here called I2. Now, if the current splits up, can I1 be greater than I? No, it has to be something less, yeah? Turns out that if you take I1, you add I2 to it, they have to equal I, right? Conservation of current. So I is equal to I1 plus I2. I'm going to box these. These are things you're going to verify today. All right, so they're like similar but opposite, right? So this one was the sum of the voltages equals the voltage of the battery. This one's the sum of the currents equals the total current. Any questions? All right, and what you'll find too is that for resistors, for in series, if you just add up the 2 resistors, R1 plus R2, you'll find the equivalent resistance or the total resistance. But for parallel, you have to use this formula. So the equivalent resistance is 1 over 1 over R1 plus 1 over R2. Right? And you'll notice that this actually decreases the resistance of the circuit. So by putting resistors in parallel, you can effectively make the resistance smaller. Why would that make sense? Well, if you give, yeah?
Not as much current is trying to go through one resistor as 2.
Right, so the current now has 2 places to go, which means it has less resistance. You've given it another path. You're not forcing it to go through the 1 resistor. You've got 2 paths, so the resistance decreases. Which is good because if you're stuck with, like, say you only have 10 ohm resistors, but you want to increase the current, you can do that. You can just start putting resistors in parallel. All right.
And the equation on the upper right, is that regular or is that RQ? On the far left, sorry.
On the far left.
Of the equation.
Oh, this is EQ for equivalent. Yes. So you can kind of like look at this whole thing here and just replace it by an R equivalent is the idea. Instead of looking at this complicated, because circuits can get really complicated, so you want to simplify them and replace them with equivalent elements. It's a good question. All right, and then I want to remind you that power, P, is equal to IV, which is the current times the voltage. So if you wanted to increase the power in the circuit, what would you do? What would be one thing we can do? Yeah, we could increase the voltage. I heard someone say it. And if you increase the voltage, you happen to also increase the current. Yeah. So add more batteries, increases the power. And the brightness of the light bulb is proportional to the power. So if you double the power, you sort of double the brightness of the light bulb. All right, any other questions? All right, you guys can get started.